semester,
Uh-huh.
first class.
Uh-huh.
I got on the wait list, and I could get on to the, and I could register for the second one, but I need to attend the first one. Which one would you prefer me to do? Do you want me to be on the wait, stay on the wait list, or register for the
What
other
number are you on the wait list?
first?
Let's stay on the wait
You'll
list.
be fine.
Yeah, you'll be fine.
And I don't need to register the other one?
Yeah, if you're number one on the wait list, then you're gonna get in.
Okay, so I don't register for
Yeah,
the
don't
other
register for that one. Yeah.
Yes.
Okay, good.
You're not even registered yet?
December 2nd.
Yeah. Well, I guess there are openings in the afternoon class, so
Yes.
that's good. Or just get on the wait list.
What if I can't get on the wait?
If you can't get on the wait list,
You let Will in. She's an A student. Let her
I
in.
know, but Chem 1B, I let too many people in this semester, so it's okay. Well, we'll see. Let's just if it ever comes down to it, we'll figure it out from there. Okay. Other questions? Raheem?
Yes. I asked Dr. Potter, I asked Dr. Bhavani.
Yes.
Is it you that's teaching Chem 1B in the summer?
No.
Are you sure?
Really?
Turner?
He doesn't teach that.
So Bonnie and Potter are not
They
teaching.
both told me no.
No. That leaves
Can't
Jimenez, Kant.
Jimenez?
teach one. He doesn't teach 1A though. He only teaches OP.
Oh, who's teaching Chem 1B in the summer?
1B.
I'm not sure,
I'm gonna ask him.
but I'm definitely not, because the first session that's an 8-week session, so I can't make it because I'm going to be gone for part of June.
One more thing.
So I'll have to double check.
Okay, Jimenez or Kant? I'll be asking around, don't worry. No, it's not because I'd rather take Chem 1B in the summer.
Yeah, Chem 1B, if you just focus on one course, is not bad.
Yeah, but it's 8 hours of lecture a day.
Oh yeah,
2 labs, 1 lab a day. That's insane.
it is insane.
Thank you.
But you can't do anything else other than Chem 1B.
Yeah.
I've taught it. I've taught Chem 1B many times
In the summer?
in the summer. Yeah.
And what's your average grade in the summer?
Well, 1B, no. A lot of people say take summer classes because they don't put as much material in.
Exactly.
So, but the 1B over the summer, I didn't take out anything. I put everything in.
Do you do weekly tests like that? A practice exam? Is that
Yeah.
what it is?
They have to.
Every week.
So every week there's a test.
Every week there's a test.
Why are you laughing?
Good luck with that.
If you're going to take one course, a 1B or a 1A, I think 1B in this would be easier over the summer, yeah, than a 1A over the summer. 1A over the summer would be very tough.
Who's teaching it? That's the.
Actually, go ask the dean. Just go over to the office over there, and she'll let you know
She'll
who's
let you
teaching.
know?
Yeah,
Okay.
I think.
The gray hair though, right?
Right, Shankweiler.
Thank you.
She's here this week.
Oh, you checked.
No, she's here. She's in the office.
All right. Any other questions? Dan?
Can you do another example of
Hybridization? Yeah. Yeah. Actually, that's what we're doing today. We're just doing examples of hybridization.
I'm doing it.
Yes.
Thanksgiving.
It is recording now.
But I need your data because on your
Yeah.
like your actual data.
I think it should be okay.
You and Chelsea.
Yeah.
Yeah, anyway.
I freed up a lot of memory on the hard drive, so I don't think it'll crash. Yeah. Well, hybridization, what we do is we look at the electron geometry. The electron geometry is going to tell you what the hybridization is. And so if you have a linear electron geometry,
SP.
it's SP. Right. Because we need 2 orbitals 180 degrees apart from each other. And so the only way you're going to get that is SP configuration. How do we get SP hybridization? We take one S and just one of the P's, and then mix those 2 wave functions. And so we end up with 2 SP orbitals and 2 unhybridized P orbitals. And so when we look at this, we can draw it. We'll just draw all the orbitals. So we have A, we got to have an SP orbital pointed to the right, an SP orbital pointed to the left. So this gives us this kind of arrangement. The angle here is 180. That leaves two unhybridized orbitals. And the two unhybridized orbitals we can show like this. Here's one of them. This is a p orbital. P orbital, an sp, these two sps look like a p, but they're totally different because each one of these lobes is an individual orbital. Whereas this is, this with two lobes looks like two orbitals, but it's actually just one orbital. One p orbital with two lobes. We have one more p orbital. Where is it?
See?
Yeah, it's going to be perpendicular to the board. So we got a p orbital like this that's sticking out and going into the plane. And so this is the second p orbital. So that's this, and then we have this green one here. And so we call those unhybridized. They're just our standard p orbitals, which are 90 degrees from each other. So this is sp hybridization. Should we do an example? No, let's just look at all the hybridization schemes, and then we'll do an example of these later. All right, what's the next electron geometry that we encounter? The next one is trigonal planar. And so what we need is, we have an atom in the center. We need three orbitals that are 120 degrees apart from each other in orientation and in a planar arrangement like these. And so how are we going to get that?
SP2.
Right, SP2. So to generate SP2, we'll take one S and two of the P's, and we'll form three new orbitals. Each one's called an SP2 orbital, and that leaves one P orbital untouched. Looking at the orbitals here, actually we can write those. Here's an SP2 orbital. Here's an SP2 orbital. Here's an SP2 orbital. So we have a trigonal planar arrangement of SP2 orbitals. The angle should be 120 degrees. This one should be out a little bit more. And so that's three orbitals here. Where's the p orbital? Yeah, the p orbital is sticking straight into the bore and coming straight out. And so this would be the unhybridized p orbital. Here it's hard to see it because you're looking at it from the top of the p orbital down, so we call this the top view. I could rearrange it so that we can see the p orbital in profile. And so what I would do is I just grab this orbital and spin it, not 100, but 90 degrees this way. If I did that, I would get this. The SP2, this stays in the plane. But this SP2 is going to pop out of the plane here. So we got one SP2 coming out of the plane, and then we have another SP2 going into the plane here. Another SP2 that's hidden. Where's the p orbital? The p orbital is now going to be in the plane, so both lobes are here. So that's our p orbital. This is looking.
Is it recording?
It is recording.
Okay.
I'm pretty sure. Yeah, it's recording. This one I call the side view because we're looking at the p orbital from the side versus from the top down. That's it. All right. After trigonal planar comes tetrahedral.
SP3.
SP3. SP3 is very common. SP3. And so what we'll have is we'll have an atom at the center, and we need a tetrahedral arrangement of orbitals. And it's going to be given by an SP3 hybridization. Let's go ahead and generate it. So one S and three of the P's. We hybridize all of these, and we'll get four new orbitals called sp3 orbitals. The energy here, it's going to be higher than S, but lower in P. Since it's 3/4 P character, it'll be closer to P than S. Okay, drawing out the orbitals. So we'll show an sp3 here, an sp3 here. So 2 in the plane, 1 coming out, and then 1 going in. This one is over here, this sp3. So those are our 4 sp3 orbitals. Okay, after tetrahedral comes, trigonal bipyramidal. Trigonal bipyramidal has 3 in the plane like this, 1 sticking out and 1 sticking in. So we need 5 orbitals here. If you recall, we labeled these. Like, for example, is this an axial or equatorial? This one that sticks straight.
Axial.
This would be axial. How about this one? Equatorial. Axial. Axial. Equatorial. Equatorial. So we have 3 equatorial positions and 2 axial positions. In terms of just space, in terms of repulsions, you know, if you have a lone pair, do lone pairs have greater repulsion than single bonds, or greater? Why? Why is that? Why would lone pairs have greater repulsion than single bonds? Not polarity. In a way, polarity, but in a way not. Why would lone pairs have greater repulsion than single bonds?
Charge of the electrons is not shared.
Yeah, the electron charge or the electron cloud is not shared. And so in a single bond, you got an atom over here, atom B, pulling electron cloud away. But if there's no atom B here, then the electron cloud gets pulled towards A, meaning it, you know, there's a higher charge density here, which is going to affect these. And so out of these, which one has more space? An equatorial with 2 90-degree repulsions and 2 120-degree repulsions, or an axial with 3 90-degree repulsions? Equatorial, because these 120 repulsions aren't that significant, not compared to the 90s. So the 90s are much more severe. And so since we only have 2 90-degree repulsions here, there's more breathing room than this axial. If we look at the axial, there are 3 90-degree repulsions, which are significant. Well, how is that going to influence this? Well, you know, in the last one, we've already hybridized all our orbitals, the S and the P. So we need more orbitals. Where are they going to come from? So we got our S, we got our 3 Ps.
The D.
Yeah, that's going to come from the Ds. Now the Ds have to be in the same N level, and so we'll just call it N, S, N, P, and D, where N is the same for all 3 subshells. All right, to get this, we're going to take 5 of these to get 5 new orbitals. So that's the F. And we're going to call these 5 new orbitals sp3d orbitals. And that's going to leave 4 of the Ds untouched. Now, do we label these sp3ds axial and equatorial? No, they're going to be the same energy, all of them. It's just the repulsions being different. And so 5 degenerate sp3d orbitals. What do they look like? If we were to draw the center atom, we'll draw an axial here, sp3d, and then an equatorial here, sp3d, and an axial here, sp3d. So we have this T shape. And then this one's going to come out of the board. This is sp3d here. And then this one's going to go in, sp3d. And so just to label it A, E, 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 equatorial versus axial. It's not electron, it's equatorial. and this is X. So let's take a look at some examples of trigonal bipyramidal.
What's the remaining? What's the remaining D?
The remaining d orbitals are here, but I don't want to draw them. You know, because if I start drawing them, the drawing gets kind of messy. Because you got to put, d orbital here, 4 lobes, and another d orbital here. The d orbitals are there. They're just not shown for clarity. Excuse me. Sometimes the d orbitals do participate. The unhybridized d orbitals do participate. We'll talk about that later. Let's take a look at some examples. PCl5 is one. PCl5, if we do the Lewis structure, 3D Lewis structure, it looks like this. In 3D, we try to show the geometry, dimensions. Like this. So this is PCl5. It's trigonal bipyramidal. We need 5 orbitals. Only way we're going to get that is sp3d hybridization. And so phosphorus must be sp3d. 1, 2, 3, 4, 5. sp3d. And how many electrons does phosphorus have in this structure? When I ask how many, we count it using formal charge type of counting. 1, 2, 3, 4, 5. 5 out of the 10 electrons surrounding it belong to the phosphorus or come from the phosphorus. 1, 2, 3, 4, 5. Where do the remaining 5 electrons come from? The chlorines. And so the chlorine is going to be, now here's where I'm going to deviate from your book. Chlorine, what is the hybridization around chlorine? We have 1 single bond and 3 lone pairs to give us a total of 4.
SP3?
It's going to be sp3. And so chlorine would be sp3 hybridized. Because the reason I'm deviating from your book is your book does not hybridize what they call the terminal atoms or the peripheral atoms. And so it didn't hybridize this, and instead it would just bond this with a p orbital. But if we have a p orbital, if we're using p orbitals on chlorine, then we're going to have 90-degree repulsions, right, between the lone pair and the bonding pair, or lone pair and lone pair, because the p orbitals are all orthogonal to each other at 90-degree angles. And to minimize repulsions, why do we hybridize anyway? We hybridize to minimize repulsions, right? And so it only makes sense to hybridize the chlorine to sp3 to make the 90-degree repulsions go out to, if we hybridize it to sp3, the 90 degrees would go to 109, right, roughly. And so that gives more breathing room for the lone pairs, correct? Now, who's right? Am I right to hybridize it, chlorine, or is the book right to not hybridize chlorine? Yeah, it depends on how. Actually, neither of us is right, because it turns out that the degree of hybridization depends on how much repulsions you have. If the repulsions are significant, quite significant, then it's going to hybridize. Hybridize to 109. 109 because you're going to get the maximum angle between all the groups. That is bonding in 3 lone pairs, roughly. But sometimes the orbitals are big, and so the repulsions aren't so huge. And so let me give you an example, like iodine. Iodine, if you look at the orbitals, the p orbitals are gigantic, right, in iodine. And so if you have a 90-degree repulsion in iodine, let's say, lone pair in this p orbital, lone pair in this p orbital, the orbitals are gigantic so that the repulsions aren't so significant. Whereas if you go to fluorine, fluorine, you have tiny orbitals, and so all that electron density is concentrated right on the nucleus. And so now when you have 90-degree repulsions, well, they're going to be significant and you need to hybridize. And so it turns out that the degree of hybridization depends on how significant the repulsions are. And so for very big atoms, we don't have to hybridize as much. Maybe we don't have to hybridize at all. But for very small atoms, we really need to hybridize those. Otherwise, the repulsions become too significant. The energy is too big. And so this, well, how do you know what's big enough? So the book gives an example. For example, H2O. What's the bond angle in H2O? It's nonlinear. Less than 109. You know, it's about 105 degrees, right? H2S. H2S has the exact same Lewis structure. So H2S, you would expect the bond angle to be less than 109, about 105 degrees. But it turns out that H2S, sulfur is such a big atom, and the p orbitals are big enough that you don't really need to hybridize as much. And so the bond angle in H2S comes out to like 92 degrees, you know, closer to 90 degrees. And so there's just a minor amount of hybridization to open up the bond angle a little bit. And so that degree, you know, we can have different amounts of mixing, and those different amounts of mixing relate to this. Pretty soon, you know, you get away from thinking in terms of, you know, 1 part S, you know, 3 parts P, like here, sp3. 1 part S, 3 parts P. Maybe it's like 1 part S and 2.5 parts P. You know, something like that. You know, different degrees. And in other words, the percentage S character and the percentage P character is variable in that way. Well, anyway, what are we going to do? Well, what we're going to do is we're just going to hybridize everything. You know, that's easy. And is it entirely correct? Sometimes it is, especially for small atoms it would be. Sometimes it's a little off, but you know, if you don't hybridize, you're still going to be off, right? And so you might as well just do it the easier alternative. The easier alternative is to hybridize everything. Did you get it?
Yes.
No? All right. You know, in other words, why did I go through all that spiel? The reason I went through all that is because so you don't think that it's always right to hybridize everything, or it's always wrong not to hybridize everything. You know, the actual situation is somewhere in there, and it's a little bit more complicated. But you know, we're just going to hybridize, and so the chlorine will hybridize, and it makes sense to do that. It's going to be sp3. We need another chlorine sp3. Another chlorine sp3 here. And so we can come up with a drawing like this. It shows the valence bond picture of this. We'll put a phosphorus in here. We'll draw one sp3d orbital like this, another here, another here. And then one coming out, and then one going in. So those are our 5 sp3d orbitals. Each one of those is singly occupied by a phosphorus electron. This. And then we have a chlorine come in. The chlorine is going to bond with what orbital?
D.
sp3. So let's take a look at chlorine. That's phosphorus. If we look at chlorine, chlorine is sp3 hybridized. It means it's going to have 4 sp3 orbitals. And how many electrons does chlorine have? 1, 2, 3, 4, 5, 6, 7. 7 electrons. 1, 2, 3, 4, 5, 6, 7. 3 lone pairs and 1 bond. I need to flip this electron because phosphorus is pointed spin up. Therefore, chlorine's got to be spin down. So phosphorus sp3d electron comes in here and bonds with it. So it's shown here. Actually, I didn't. Let's make these all blue. have a bond. What kind of bond is that? Yeah, sp3d, sp3 sigma bond. Now chlorine is going to be sp3 hybridized, so there's going to be an sp3 orbital out here, and then one out here coming out of the board, and then one going into the board out here. These are our 4 sp3s. So you should have 3 lone pairs here. Be chlorine. Now, drawing all 5 chlorines on here can get kind of messy. You could do it. Or what you could do is just show one of them and the others are going to be similar. 2 in the plane, and 1 sticking out, and 1 going in. Actually, let's make the 1 going in. So lone pair here, lone pair there. So another sp3, sp3d, all these are sp3 orbitals here. And chlorine here. Show that one. And 1 in the back here. This is sp3. This is sp3. So we have 5 sigma bonds, all sp3, sp3. Okay, this is phosphorus pentachloride. Take a look at another one. Look at sulfur tetrafluoride. Sulfur tetrafluoride is going to have a Lewis structure that looks like this. We're going to have 4 bonded atoms. So let me just draw the positions here. I'm going to erase one of these. And 1 lone pair. Where should we stick the lone pair? We aren't going to put it on this, although it might not be a bad idea. We're going to put it in this equatorial position here with the lone pair. That's going to be in the plane. The reason we do it this way is to show the symmetry of this molecule a little bit better. And
Oh, it's a seesaw.
yeah, this is the seesaw geometry. Seesaw. The reason it's called a seesaw is if you tilt this, so it stands on these 2 fluorines, then it will look like a seesaw. Now, let's talk about the, before I get to that, let's just take a look at the angles here. In something like PCl5, do you expect any distortions of the angle? No, and so we're going to have 3 angles here. We're going to have the axial to axial angle. The axial to axial angle should be 180. And then we'll have the axial to equatorial, 90. And then the equatorial to the equatorial, 120. So we got the 3 angles, 90, 120, and 180. Over here, the angles are going to be distorted because of this lone pair. And so let's just take a look at these angles here. I'm going to label the fluorines axial and equatorial. So we have 2 equatorials and 2 axials. So just quickly, it's not a perfect seesaw because it's going to be bent a little bit. And so let's take a look at the axial to axial. In a seesaw, you want this to be 180. And so if we go fluorine axial, sulfur fluorine axial, the angle should be 180, but it's going to be squeezed in by this lone pair. And so it should be less than 180, a little bit less than 180. And so now let's look at the axial to equatorial. This should be 90. So fluorine, sulfur, fluorine, equatorial. angle. Should be 90, but it's going to be distorted because of the lone pair pushing it. And so it'll be less than 90 degrees. And then let's look at the equatorial to equatorial. So fluorine equatorial, sulfur fluorine equatorial angle. This should be 120, but it's going to be distorted. It's going to be less than 120 because of the lone pair electron cloud distorting or pushing the other electron clouds in. So here, what's the hybridization on sulfur? Sulfur is, well, it's got 5 groups, so how can we get 5 orbitals, equivalent orbitals? Well, we need s, p, 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 d. This is sp3d. Hybridization. How many electrons does sulfur have? Yeah, 1, 2, 3, 4, 5, 6. So let's go ahead and fill these in. 1, 2, 3, 4, 5, and the 6th will pair. So it's got 1 lone pair. That makes sense. And then the fluorines are going to come in. What's the hybridization on the fluorines? What is the hybridization on fluorine? sp3. So fluorine sp3 comes in and bonds here. Oops. Not the lone pair. Another sp3 fluorine. 4 of them come in, bond here. So if we could draw this out in a valence bond type diagram. So we'll have sulfur sitting in the center. There's going to be 5 sp3d orbitals. 1 here, equatorial here, another axial here, and then an equatorial coming out, and 1 going in. Looking at the electrons, you know, this got a lone pair here, electron here. And then what's going to happen? The chlorines are going to come in, bond to it. Let's go ahead and get some chlorines in here. Just do it blue. Not chlorine, sorry. Fluorine sp3 here, here, here. Fluorine sp3, fluorine sp3, fluorine sp3. Okay, that's it here. And then this cloud is going to be more concentrated on the sulfur, which is going to push these clouds in a little bit. 4. Let's look at another molecule. Let's see. BR3. Let's see, ICL3. Let's try that. See what we get. How many electrons do we have here? It's like 4 times 7 is 28. 28 electrons. Draw up a loose structure. What goes in the center? Probably I. I is a big atom. Right? I is probably going to be attacked by the chlorines. So let's go ahead and attack it. I'm going to write it like this. And there's 2 lone pairs here. 1, 2, 3, 4, 5, 6, 7 here. then the chlorines each have their arquettes filled. And the reason I write it like this is to show the geometry a little bit better. If you look at this chlorine here, actually first, what is the hybridization on iodine? It's sp3d. We got 5, 3 bonds and 2 lone pairs, 5. We need 5 orbitals. So this is sp3d hybridized. If that's the case, is this chlorine axial or equatorial?
Axial.
This is going to be axial. This is equatorial. This is axial. Now, why did we label it like this? Why did I put the 2 lone pairs in the equatorial and not the axial? To minimize repulsions, right? If I put the lone pairs in the axial, then I'm going to get more significant repulsions. And so I just picked 2 of the equatorials. They're all the same. So just 2. This is to show, you know, these solid circles are to show the lone pair projecting out. These dotted circles are to show the lone pairs projecting in to the board. And so this is our sp3d hybridization for iodine. Iodine has how many electrons in here? 7. So the iodine, sp3d, there's 5 sp3d orbitals. S, 3 p's, and a d. That's 5. And 7 electrons, 1, 2, 3, 4, 5, 6, 7. So we should have 2 lone pairs and 3 bonds. The bonds are going to be to chlorine. What's the hybridization on chlorine?
sp3.
sp3. And so here, 1 chlorine comes in, another, and another. All these are sp3 chlorine. If we want to see this from chlorine's perspective, we could do that. Chlorine's sp3 hybridized, so we got 4 sp3 orbitals. So chlorine has how many electrons? 2, 4, 6, 7. So 1, 2, 3. I'm going to make this one spin down. 4, 5, 6, 7. So that's 7. I made this one spin down because iodine comes in and bonds with it using sp3d orbital here. So let's draw it. Well, we'll throw the iodine in the middle and then have my 5 sp3d bonds. I mean orbitals. 2 lone pairs, and then 3 singly filled, singly occupied, sp3d. This lone pair is projecting out, this lone pair is projecting in. And then complete it with chlorine. Chlorines are sp3s. Two in the plane, 1 coming out, 1 going in. Have here. So sp3. And so sp3, sp3d sigma, sp3d, sp3 sigma, and then 1 more here, sp3, sp3d sigma. Completes it. And so this is this going to be a perfect T?
No.
No, it's going to be distorted. So let's do the angles over here on the Lewis. The axial to axial. So if we go chlorine, iodine, chlorine, axial. Axial to axial angle should be, it's supposed to be 180, but we're going to expect it to be less than 180. It's going to be pinched in a little bit this way. Right? We measure by the shortest angle, not the longest angle. Always. What is the shortest angle possible? And then we're going to have chlorine axial to chlorine equatorial. You know, this angle should be 90, but it's going to be pinched in, so it's going to be less than 90. Let's do another. Here. I'm going to do xenon dichloride. Xenon's a noble gas, so it's not terribly reactive, but xenon's also.
Wait, how would you know if like an element is like an sp3d or an sp3?
How would you know?
Yeah.
How you know is how many groups you need to accommodate. And so I need to accommodate 1, 2, 3, 4, 5. And so you just count it. S, P, 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 D.
Also that includes lone pairs.
Yeah. You have to include the lone pairs too because you need orbitals to accommodate that. Now you treat lone pairs and single bonds equally. And the same thing you do with double bonds. Even though it's a double bond, you don't count it twice. You just look at. We're going to look at some examples of this later, but look at how many groups. So double bond is counted as one group of electrons, and triple bond is counted as one group. And so we need to accommodate 5 groups of electrons. That means sp3d. If we only have 4 groups, here we only have 4. Lone pair, lone pair, lone pair. 3 lone pairs and 1 single bond, which means, what's the hybridization? So 1, 2, 3, 4. We need 4 orbitals, right? S, P, 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 sp3. It's got to be get you 4 orbitals. That's how we know. Mm-hmm.
How do we know there are 3 bonds around ID and 2 pairs?
How do we know? I skipped some steps. You know, first we try to draw the Lewis structure. After going through all the steps of drawing Lewis structure, this is what we'll come up with. That there are going to be 3 bonds and 2 lone pairs. Look at the formal charges in the structure. What are the formal charges? They're all 0. And so this structure turns out to be the best. Sometimes there's alternate structures that you can come up with. In this case, this one should be the best. Only
How
one.
do you know when to expand the leadership? Because those structures always expanded leadership.
Okay. How do you know when to expand the valence shell, the octet? Have you been reading the book?
Yeah.
Yes.
But you didn't
Okay.
mention.
All right. There are 2 thoughts on this here. And more work needs to be done. Remember I told you that in chemistry, not everything is really well understood? Well, the bonding here is not really well understood because quantum mechanics, right, is the foundation for all this stuff, mixing wave functions and all this other stuff. Well, recently, people have been doing rigorous quantum mechanical calculations on this type of thing. And what they're finding is that, you know, here, if I mix an S, you know, this is 1 part S, 3 parts P, 1 part D. And so that's 1/5 D, which is 20% D character in this orbital. And so if I have this new wave function, I expected 20% of that hybrid to be D, you know, the hybrid to be D. When they did the quantum mechanical calculations, they found a much lower, much lower percentage of D character than what is expected here, right? And so they found that there wasn't as much mixing of the D orbital into the hybrid as was once thought because the percentage is really small. And so this is the ad hoc kind of thing. This has been, this has been taught for a long time. So the ad hoc thing, ad hoc is after the fact, you realize, there isn't that much D, and we're predicting 20% D characters, and there's got to be something else going on, right? And so the alternate explanation to this, let me just talk about this. This is advanced topic. First, we're going to learn it this way, and then we're going to talk about the advanced topic. But now we're going to talk about the advanced topic. The alternate way of explaining this guy is not to expand the octet, is to leave the octet and do this. We got too much electron density. How much? We got 2, 4, 6, 8, 10, right? We got 10. And so the other way to do this is to just leave the octet. We leave the octet there. Like this. And the structure is still going to be the same. And so we leave the octet there. But how does this third chlorine attach? This goes for PCl5 as well. So you can imagine the same thing happening in PCl5. Now, how the heck does this third chlorine attach? There's no bond, right? But I'm missing some electrons. The electrons that I'm missing are this. So we leave this. Now iodine only has an octet, 2, 4, 6, 8, right? And how is this third chlorine held on? Well, what is the charge on that third chlorine now? Because now chlorine has all the electron density, all the electron cloud, which means the charge on this chlorine is -1. And what is the charge on iodine now? Plus. And so the current thinking regarding these expanded octets is it's a mixture of covalent and ionic bonding. And with this, you could actually draw how many resonance forms? 3, right? And so what it is each of these bonds has a certain percentage of ionic character and a certain percentage of covalent character.
And the covalent character is always octet.
Yeah. Well, the covalent character would, because these are lone pairs, so that's not really covalent. But it gets away from our thinking, this. There are different degrees of hybridization, just as there are different degrees of percent ionic and percent covalent character. The things that we typically think of as being highly ionic are metals and nonmetals. And so what we start doing is we start veering away from, this is ionic, this is covalent, and start looking at, what is the percentage ionic character in that. And so what we do is we plot percent, what did we do? We plot percent ionic character versus delta EN. Delta EN is the difference in electronegativity. And we see there's a rough correlation here. If you look at the R squared, it's not that great because it's not, well, actually it's not that bad either. But the function is there's a lot of scatter here. I think the R squared is like 0.7, something like that, 0.8. And the general trend is this. The general trend is as the difference in electronegativity gets greater, the percent ionic character increases. There's less sharing. That only makes sense because if the difference in electronegativity is great, then one of the atoms has a much stronger pull for the electron density. But there are some outliers here. Not everything fits perfectly. There are some things with a pretty big difference in electronegativity, but not as ionic as you think. And so there's like a continuous variation from 0% ionic to, not 100, but close to 100% ionic. Well, this is a little bit different. This is the chart in your book here. Now, this one, the advantage here is we don't have to invoke an expanded octet. We don't have to We don't have to get any D character in here. Okay. And so this, more work needs to be done, to really understand. What you do is, electron clouds are they're like water; they just want to spread out. And so we're gonna get a resonance hybrid, and we're gonna see negative charge density on the chlorines, positive charge density on iodine, and there's gonna be some kind of percent ionic character in there. This is not anything unusual, because we know for sure that there's going to be percent ionic character in here by looking at the oxidation states. If you look at the oxidation states, it's clear that there's got to be some kind of, this isn't a perfect sharing. This isn't a perfect sharing arrangement. What are the oxidation states here? Yeah, let's take a look at the oxidation states. We got -1, -1, -1, +3. Iodine is a halogen. Is it all that happy in the +3? No. And so just looking at the oxidation states, there's got to be, there's some charge separation. Whenever we have this charge separation, there's going to be electrical attraction between positive and negative. And so based on the oxidation states, there's got to be some degree of ionic bonding. Remember, oxidation state assumes what? 100% ionic. Formal charge assumes, what are the formal charges? They're all 0, right? And remember what I said. I said, which one is right? Formal charge or oxidation state? Neither. It's somewhere in the middle, somewhere in between. And so it's not 100% covalent, it's not 100% ionic, it's some kind of percentage in between. So there's some covalent character and there's some ionic character. Now, how is it best to show this? And so, this is one way of showing it, the covalent and the ionic, but this is a little extreme because this is now 100% ionic here, just for this bond. So we're going to come up with some hybrid, and how does the hybrid correlate exactly with all this? And so this is one way to show, okay? So let me go back to what I said. What I said was, first we're going to just do what? We're going to hybridize everything. And so what is this hybridization? It's sp3d hybridized. And then later we're going to pick up the little nuances here and there, which are a lot more complicated, right? It's easier just to learn it one way first and then figure out, wait, there's some limitations to that. But as long as you have a good solid, because I don't want to confuse things right now, so as long as you have a good solid understanding, sp3, and then you got to think, okay, now why didn't Petrucci hybridize this? Forget it. You don't have to worry about why Petrucci didn't hybridize it. He has his reasons, but I have my reasons for hybridizing it as well. Okay, so we'll just hybridize everything. Then you got to realize, well, is that the ultimate answer? No. It's a little bit more deeper than that, right? That's all. Okay. All right, let's do another one. Here, we're going to do XeF2, xenon dichloride. Xenon is a noble gas, so it's an inert gas, but in this case it reacts with fluorine. Why would xenon actually want to react with anything? Right? Noble gases are unreactive. It's so big. It's so big, its ionization energy isn't so great, like helium. Helium's impossible to react with. Neon, same thing. Argon, krypton. Krypton maybe, argon no. You know, those are small. But fluorine can actually attack xenon and react with it. It's big. And so when that happens and you draw the Lewis structure, we're going to draw a Lewis structure something like this. We'll put the fluorines here. And then xenon. All right, what is this? Hybridization on xenon. sp3d, right? sp3d, which means it's trigonal. It's trigonal bipyramidal. Except that's the electron geometry. Electron geometry is trigonal bipyramidal. But its molecular geometry is... Actually, well, you know, I forgot to write the last one. This one. What is this shape? Can you see it? No, this is T-shaped. Got the 3 chlorines forming a T. Did I talk about it? Did I forget to write it down? I forgot. This shape is T-shaped. Do you see it? Because we don't count the lone pairs. The lone pairs are there for sure, and they're causing this T shape. But we just look at the atoms, and the atoms are in a T configuration. It's not a perfect T, it's a distorted T. And so if we look at the axial to equatorial angle, you know, a perfect T would be 90. This angle is going to be less than 90. Angle here. And then if we go axial to axial, you know, this angle should be 180, but it's going to be less than 180. And so it's a little distorted. You know, it's less than 180 this way. You know, it's being pushed in this way. So this angle on the left is bigger than 180. This angle on the right is smaller than 180. But we always pick the smallest angle. And so it's less than 180. Okay. And so it's kind of a distorted T like this. Right? That's how it's going to look. Like this.
Will that be bent?
This one is not bent. This one's linear. And the angle is 180. There's no distortion.
But there's two sets of electrons on both sides, whereas
Yeah, it's just because of my drawing. The 2 sets of electrons are like this, right? But when you look at it, it's equal. So, you know, the repulsions aren't going to push it one way or the other. It's all equal. And so there's no distortion here. It's just linear. And what's the hybridization? sp3d. And, you know, we need an sp3d orbital here, an sp3d orbital here coming out, sp3d orbital going in, and here and here. We got the 5 sp3d orbitals. When we do xenons, let's just do the energy level diagram. When we do the energy level diagram, xenon is sp3d, which means 5. 1, 2, 3, 4, 5. How many electrons does xenon have in this structure? 8. So 1, 2, 3, 4, 5, 6, 7, 8. So 3 lone pairs, 2 bonds. The fluorines are going to come in and bond. Fluorine is what hybridization? sp3. Another sp3. Since there are only 2, I'll write it all out. I didn't show the, you know, I could show the orbitals here. But now we're going to move on to to an electron configuration that's octahedral. Octahedral, you have an atom here, and then there are going to be 6 bonds or 6 electron groups attached to it. It doesn't have to be bonds, it could be lone pairs, it could be double bonds. 6 of them though. Now we need 6 orbitals. How are we going to get 6 orbitals? Well, S is 1, and then P's, that's 3, so that's 4 orbitals. I need 6 orbitals to hybridize. Yeah, I have 5 Ds, so I'll just take 2 of them. And that gives me 6 orbitals that I can hybridize to come out with 6 new orbitals. The 6 new orbitals are going to be called sp3d2. Just see what those look like. Those will look like this. Up here, an sp3d2 up here. sp3d2. And then I'm going to draw like this. One coming out this way, sp3d2. One going in, sp3d2. One coming out, sp3d2. And then one going in back here. And then one coming down. And so that's 6 equivalent orbitals. Should I label this one axial? These 2 axial and these 4 equatorial. Should I label that? No. The reason I'm not going to label it is this axial has how many 90 repulsions? 1, 2, 3, 4. If I grab an equatorial, how many 90-degree repulsions am I going to have? No, actually 1, 2, 3, 4. And so, you know, whether it's axial or equatorial, it has the same 4 90-degree repulsions, 1 180. And that means that the axial and equatorial are exactly the same. And therefore, if we label them differently, that's not correct. They are exactly the same. In fact, octahedral has a special symmetry. We call it spherically symmetric.
Like tetrahedral.
Or like tetrahedral. Octahedral and tetrahedral are both spherically symmetric. Same in all directions, isotropic. All right, now let's, it's not totally isotropic in that, you know, if we look here, there's nothing. But if we look here, there's an orbital. So let's take a look at an example of this. An example is SF6. SF6 tries to maximize its bonding, so we come up with a Lewis structure, 3D Lewis structure. I'm not going to draw the lone pairs on fluorine in 3D. Sometimes I've done that in the past, but let's try to just show it around sulfur. Knowing that the lone pairs are going to want to minimize repulsion, so they'll probably adopt the tetrahedral configuration. And so this sulfur is sp3d2. So let's go ahead and draw our 6 sp3d2 orbitals for sulfur. How many electrons does sulfur have in this structure? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 singly occupied. And then the fluorine sp3s are going to come in and bond here. So we'll form 6 bonds. Yes. So let's go ahead and draw the valence bond drawing for this. So we'll throw in the sulfur here. That would be sp3d2, 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 and sp3d2. So all these are sp3d2s. I'm not going to label each one this time. These are all going to have one electron in them. So there are 6. And fluorine sp3 comes in and bonds. sp3. So I'm not going to label all these. These are all sp3s. It doesn't look so good. Redraw this. One coming out and then one going in. All right, and then we just repeat that. Fluorine here, fluorine back here, fluorine here, here, here. Something like this. It's kind of hard to draw.
So that's the image.
I think maybe get the point there. All right, what are the angles here? Should we say axial to equatorial? Axial to equatorial? No. We have to come up with a different system. The different system we're going to do is fluorine, sulfur, fluorine, adjacent. You know, adjacent means next to each other. So here, that angle should be 90 degrees. What would you predict?
Greater.
Greater than 90 degrees? Less than 90 degrees? Or equal 90? Equal. There should be no distortions. And then fluorine, sulfur, fluorine, opposite. And so if we just pick 2 that are opposite, the angle should be 180. Any distortions? No, it is 180. So this is undistorted. There are 2 angles in octahedral configuration, 90 and 180. There's no axial, there's no equatorial. Bromine pentafluoride is next. Let's go to bromine pentafluoride. I'm going to draw the 3D Lewis structure. So after some time, you'll come up with a Lewis structure, and then you might try to draw this 3-dimensionally. The reason I drew it like this is to show its molecular geometry. You know, SF6, this is called an octahedral molecular geometry. What's the difference between molecular geometry and electron geometry?
Molecular is like the atom.
Yeah, molecular just deals with the atom. And the electron geometry looks at the electrons as well. But over here, the molecular geometry, this one is called square, pyramidal. Square pyramidal, because there's a square base, it's pyramid. This is square pyramidal. And so this is why I stuck the lone pair here. Did I put the lone pair? Wait a minute. Lone pairs, do they go in the axial position? Aren't they supposed to go in the equatorial position, the lone pairs? Yeah, there's no, I mean, if I stuck it here, there'd be 490s, right? So it doesn't matter. So I stuck it here. There's no such thing as axial and equatorial in octahedral. And so this is fine. But in trigonal bipyramidal, you would not stick them here. You would pick a equatorial position for trigonal bipyramidal. All right. What are we going to do about the bond angles? You know, well, what we do is we'll number them like this. I'm going to call this fluorine 1, and these are going to be fluorine 2s here. And so let's look at the angle between 1 and 2. So this is going to be fluorine 1, just the bromine, the fluorine 2. What's this angle? Well, this angle is supposed to be 90, but it's going to be distorted because of the lone pair here. So it's going to be less than 90. How about the fluorine 2, bromine, fluorine 2 angle?
Let's say 120.
Not 120.
Less than 180.
Less than 180? Less than 90? Yeah. This will be less than 90. There's confusion there. Why? Because there's 2 of these. There's the fluorine 2, bromine, fluorine 2 adjacent. That should be 90, but it's going to be less because of this lone pair. And then there's the fluorine 2, bromine, fluorine 2 opposite. And so if we look at 2 opposing fluorines, they should be 180, but because of the distortions, it's going to be less than 180. Is this molecule polar? Yes. Yeah. The bond dipoles don't cancel, so these ones in the plane do cancel, so the net bond dipole points up. So it's a polar molecule. Fluorine is more electronegative. Whereas SF6, is SF6 polar? No. SF6 is like this spherical, and it's not polar. SF6 turns out to be quite stable, actually. A lot of bonds there. Now, what's the hybridization on bromine? SP3D2 is correct. So bromine 6 would be SP3D2. How many electrons does bromine have? 7. 1, 2, 3, 4, 5, 6, 7. So that creates 1 lone pair and then 5 singly occupied orbitals, where fluorine in the sp3 electrons can come in here to create the sp3d2 sigma bond. If we wanted to draw this out, the orbitals here, bromine, we got our 6 sp3d2s. This bottom one's going to have a lone pair, the rest are going to be singly occupied. This. Then the fluorines are going to come in here, four of them. 1 here, 1 here, 1 here, 1 here, 1 here. And then there's more. Right? Etc. You can complete this on your own. Yes? Yeah, finish this later. We want to talk about one more here. And that's going to be XeF4. XeF4, xenon tetrafluoride. Another xenon compound. when we come up with xenon tetrafluoride, this is the way I'm going to draw it. One lone pair here, one lone pair here. And then fluorine. Fluorine. So when I put one lone pair, I need to put the lone pair opposite. The two lone pairs must be opposite. Why? Yeah, the two lone pairs, if they're adjacent, then there's a 90 repulsion. Here we're going to have a 180. And so two lone pairs opposite, not adjacent. Gives us this structure. What do we call this structure? Just the atoms. Square. This is called square planar. Square planar. This is the side view of the square planar arrangement. If we were to look at the top, usually write it like this. With one lone pair coming out of the board, one lone pair going in. So these are the two lone pairs. This would be the kind of the top view for this. And so xenon, what is the hybridization on xenon here? Xenon would be sp3d2. 1, 2, 3, 4, 5, 6 orbitals. How many electrons does xenon have? Usually you just look, you know, I see two lone pairs, so I'll just write two lone pairs, and then I see 4 bonds. Yeah. We always fill this after the fact, you know. We never do this first and then this. It's always this, see what the bonding is, see how many lone pairs, and then this. And the fluorines will come in, 4 of them, with the sp3, sp3d2. What kind of bond is that? Sigma bond, right? And then we could draw this out. Xenon, lone pair in this orbital, lone pair in this orbital, and one orbital coming out, orbital going in, one orbital coming out, one orbital going in. And then the 4 fluorines coming in here. This. Then you could complete the orbitals here. So sp3s. All right. Those are the hybridization schemes. We also have linear that's possible. Let's say if we have 4 lone pairs and 2 bonds, then it would be linear. Square planar. There would be no distortion. So let's talk next about bond length and strength. Bond strength. Single bonds, what do they range from? They range from, single bonds range from like 70 to 300 picometers, something like that. Look in your book. And so single bonds are going to range, you know, for example, hydrogen will have a very short. You know, hydrogen's a 1s, 1s. We don't need hybridization, do we, for hydrogen? No. It's 1s, 1s, H2. Iodine's going to have a much longer bond. You know, if we look at iodine, iodine is like this. What are we going to do with iodine? Are we going to hybridize it or not hybridize it? we're going to hybridize it. Even though iodine is a huge atom, or yeah, iodine is a huge atom, so our repulsion's very, very strong. No, because the orbitals are quite large. But nonetheless, we'll go ahead and hybridize it. So when we look at iodine, one iodine's here. It's got this gigantic sp. What is it? Sp. So hybridization on iodine. sp3. sp3. This is sp3 sigma bond. Now, when we look at the electron density, yeah, in hydrogen, we've got 2 electrons worth in this cloud. It's going to be quite concentrated, right? But if we look at iodine, this is a huge orbital. The electron density is going to be not as concentrated, is it? And so, comparing the two, yes. This is going to be a much stronger bond and shorter. This is going to be a much weaker bond and longer. Yeah. The bond energies here are going to vary dramatically. This is greater than 400. This is 436 kilojoules per mole.
Wow.
Which means UV, right? At least UV. This is more like 100 and something kilojoules, about 100 kilojoules per mole. 100 kilojoules per mole, is that very strong? No. In fact, you know what could break it? Visible light can break this. So if you have iodine, you need to protect it from just your light bulb. Because if you have your light bulb on and you're shining it on iodine, well, it can start breaking the bond. Now, this is what I mean by, are the repulsions all that significant? Now, do we really have to hybridize this to get the lone pairs away from them? Wow, these orbitals are huge, right? These sp3s, so repulsions aren't going to be as significant, so the percent hybridization is probably going to go down. And so this is be more like unhybridized rather than hybridized orbitals. Does that make sense? Now, what exactly is that percentage? We can get an idea of what that percentage is just by looking at the angles. 100% unhybridized is 90 degrees, right? Hybridized, 100% hybridized is 109. So based on where it is between 109 and 90, that gives you your percent hybridization. Does that make sense? Okay. Well, we can draw the other orbitals here, the three lone pairs here. Remember, tetrahedrals, 2 in the plane, and 1 coming out, and 1 going in. So we draw those. Now, oops, we're out of time. I didn't finish. That's odd. So I had more time in the afternoon than in the morning. But I'll talk about double bonds next and triple bonds in more detail. And then tomorrow